Hey everyone, Will Brewer here, HVAC Application Engineer with ABB. In this video, I will cover discovering BACnet objects in variable frequency drives, some analog and binary points that you are probably familiar with, some maybe you might not be aware of, and some you definitely want to make sure you have on your operator workstation graphics. As a user, designer, or programmer of a building automation system, what equipment information should you discover over a communications network, then assign to programming points and graphics to quickly see the status of your building and equipment? For this video, I will do a high-level review of BACnet objects with the ACH580 drive and using an example of all controls and monitoring over the communications network. For configuration of the drive over the BACnet protocol, see other content available online for this setup. Next, we'll look at which objects are a must for controlling the basic functions and monitoring the typical BAS status points for variable frequency drives. Then, which analog, binary, and multi-state points are optional but very useful for providing additional information related to your HVAC-R system. Finally, we'll take a look at trending or data logs to further understand the operation of the building system. As building owners, facility teams, design engineers, or controls techs, what should you see in the different types of HVAC-R systems in your BAS and graphics to see a quick reference of all the important information to understand what's going on with your variable speed drives, motors, fans, or pumps? Here are a couple of examples of systems involving drives that vary the speed of the motor to reduce energy usage or improve space comfort. For this example system, I will be setting up all controls over BACnet MSTP with no hardwired start-stop and speed reference. The following control and monitoring could be through either a BAS supervisor for integrating a drive into your network or a field programmable controller and mapping points directly to or from the drive. When working with the ACH series of drives, you will find our BACnet object numbering is consistent between products. When upgrading from a 550 to a 580, the BACnet point mapping will stay the same. If you use a VFD block or template between an ACH580 and an ACH180 for the points available, again, those object numbers align. However, if changing between drive manufacturers, while these are common points available for VFDs, it's likely the point mapping could vary. Consult your drive's user manual, BACnet pick statement, or integration guide for those BACnet points lists. One exception to the physical wiring will be the safeties, which should always be hardwired to the drive. Safeties will be functional then when using the hand mode for troubleshooting or diagnostics and maintenance, while BACnet control is only in the auto mode. Now let's take a look at mapping the binary points that you must have for controlling the drive and receiving the typical status feedback for a BAS. In these examples, I'm using the ABB Smart Buildings software CX Pro HD to demonstrate the BACnet point mapping between the Smart Buildings controls platform and the ACH580 drive. On the left side of the screen will be where we see the BACnet block for both binary and analog objects. Connected to those blocks will be command or set points written to the value in, or wireless tags providing labels to the value out. When a block is selected, on the properties screen, we will see general information such as the block type, as well as the BACnet object number within the controller. This value is assigned and incremented as you add more blocks to your program. I'll have the name that relates to the value in, titling the block, and its current status to my controller. For inputs, again, this is the command value coming in from the separate block in the program for the start-stop command and the value type. Under the constant section, this is where my device instance ID is set, mapped to the drive, as well as its object instance for binary value 10 to be the start-stop command. I can also see COV, write or read frequencies, and the property values. Here I might adjust the write frequency to happen at a shorter interval to have the drive react faster on an update of the value. On my status points, I might lower the read frequency to update changes to that value quicker. Or for analog points, I might adjust the COV increment to better match the type of data point I'm looking at. Under the write priority, you might change this to a higher priority to overwrite other commands from different parts of the program, or limit users' ability to override at a higher priority as well. Our first point is the start-stop command will be a write to the drive from the BAS. Here you can see the command coming in, writing to binary value 10. The list of binary and analog object IDs, again, can be found in the firmware manual for quick reference. When setting up your graphics or your BAS, it is a great first step to do the point discovery and name all of your points as you want to see them in the final graphics, as well as set your units. Next, we have the monitoring points. Here we can take a look at the physical status of our digital inputs. My example here, I have shown digital input 4, 5, and 6. These are the default or typical inputs for our start interlocks. Here you would have physically wired in a high static pressure switch, or a freeze stat, or a vibration switch. Independent of what is wired in the drive, you can see from the physical status the state of that start interlock. Next, you can have status of your run start feedback. Rather than using physically installed current sensors to measure the actual output of the drive, you can know the intended output from the drive itself. Finally, we'll want to monitor the fault status to know why the drive is not running, if it's related to a condition that the drive has stopped or prevented itself to run. For analog points, the must-haves for controlling the drive will be the speed set point output. Here we have the point for writing into the speed set point in percentage, mapped to the analog value 16 of the drive for input reference 1. This will be used to vary the speed of the drive depending on the programming controlled from the building automation system. For monitoring, we will have an output for the frequency of the drive to provide the status that the drive is running at the speed commanded. If you were using PID control, you could monitor this also as a feedback to know that the drive is modulating following changes in the feedback. For an easy indicator of the drive status, you can also monitor the actual output current of the drive. Again, this can replace the need to have a current transducer on the motor output wires of the drive to try to gauge the status of how much the motor is working to move the fan or pump. This can provide information back, such as if current were to suddenly drop to a low number but the drive was still running, that there was some loss of load at the output, perhaps a broken belt to a fan from the motor. If the current is increasing a little bit over time, maybe filters are starting to load up, causing a pressure drop. And another great output for monitoring would be AV6 for instantaneous power output of the drive. This would be your kW of the drive to have an idea of the amount of energy being used by the system, whether it be fans or pumps. Another consideration for BACnet monitoring is the BACnet property COV, or change of value. This parameter of any BACnet object instance can be a range from small to large depending on the point type. Things to consider when looking at COVs are the type of point and the update value you need to see depending on if it's power, current, frequency. For example, when looking at variable frequency drives, if you have a smaller drive that uses less amps than a larger drive, you might want to see the current change in a smaller increment, such as 0.1 amps. For a larger drive that may run up into the 100 amp range, maybe you only want to see it change every 1.0 amp. However, in larger systems, more frequent point updates with change of values at smaller values will create more traffic on the network, slowing down the overall communication rate. So this will have to be a balance between how frequently you want to see the values update and how quickly you want your network to run. Now that we have the must points set up for control of the drive and monitoring the typical status points, let's take a look at the optional points available with the drive to further take advantage of the integration available with the drive. For the drive relay outputs, these can be mapped directly to be controlled over the BAS. This could be useful if you wanted to use the relay output from the drive to control a device that's maybe closer and easier to wire to, or if no more output points are available on the existing control system. Similarly, we could use the digital inputs to monitor additional status points back if easier to get to the drive or no more are available in the building control. Here, we're going to monitor hand auto status. This is a great point to see the actual feedback from the drive to know that it's in the hand mode. This could be a condition where you see the fan or pump running at a constant speed and not following the building schedule of turning off. It is an easy indicator to know that someone has just accidentally or inadvertently pressed the button on the keypad and someone just needs to go put the drive back into auto mode. You can see warning status to know if there's a condition that the drive is in where it's running beyond its normal limits and a fault could happen soon, or any other state that may be preventing the drive from running that needs to be addressed. On my demo unit, my example will be opening the start interlock for the drive, and now I can see that the warning status is true, preventing the drive from being able to run. Another great option available over the comms network could be the direction set, to be able to reverse the direction of a fan or motor or pump. For example, when needing to do de-icing control for a cooling tower, we can adjust this over the comms network with logic in the BAS. And finally, if the drive has faulted and stopped, and you're comfortable with being able to reset the drive remotely on a number of faults that are available to do over comms, this bit's available to send a reset command to the drive and attempt to run again. For analog points, let's start with AV2 for DC bus voltage. This is one we commonly use to make sure that the input voltage to the drive is within its ideal range for the application. Next is the VFD temperature. This one's becoming more common and can be confusing without understanding the actual application or intention of the point. For the drive heatsink temperature, it is in percent of limit for the drive. In my case, the drive is at 19.7% of its total temperature range. We have chosen to show the temperature in percentage of limit to know that as you approach 100% is when you are going to be in a condition where the temperature of the drive could be an issue, as opposed to a degrees Celsius or Fahrenheit where you might not know what is the high or low limit. Kilowatt hours can be tracked as either a resettable value or a cumulative value of the drive. Here I am looking at AV9, but if I change this to AV8, I will have a resettable counter that I can send a command to the drive and reset to just see the kilowatt hours of a reading over a specific period, for example, each day. Next is the drive running hours. This can be used to track how many hours over a period that the drive is actually running the motor, fan, or pump. Two examples worth noting are the mailbox points. These can be used to write a parameter you want to monitor and then read out the value if they are not included on the default BACnet objects list. Next, we have the analog outputs. Similar to the relay outputs, we can use these as field connections for devices that could be controlled as pass-through points from the BAS to the drive to control equipment in the field. And then monitoring the status for analog inputs. These can be a very useful point to monitor to understand if you have an input reference wired into the analog inputs or are using them for sensor inputs or feedback to the drive. For example, if, again, the drive is set up in a PID control with a temperature or pressure feedback, we can monitor that status to know what condition the system is in while the drive is running at varying speed. If your BAS controller includes multi-state input, output, or multi-state variable blocks, We recommend using these points available in the drives. Multi-state points allow text to be assigned to either a binary or analog value and can be read across the communications network instead of having to assign your own values or enumerate analog values coming from another controller. Here in our drive, we have 3 different types of multi-state values. Earlier, I mentioned using the hand or auto mode status binary point to monitor the mode of the drive. If looking at multi-state value 0, you could actually see if the drive is off in hand, auto, or being overridden. For faults, you could read a variety of fault text states rather than the analog value and have it to interpret from our firmware manual the fault condition or the binary value of true or false. You can see the current and last 2 previous faults, as well as the warnings, where you can see a variety of warnings, current and the last 2 active warning. One more BACnet point I would like to give additional consideration is BV26, or underload monitor. This point is a trigger for the user load curve that is calibrated to monitor the torque output of the drive. For our applications, this could be used to indicate a broken belt situation. Typically, specifications or traditional installs have used a current sensor on the output of the drive to measure when the motor load has dropped down to a level lower than the normal amount required to turn a fan. In variable speed applications or adjusting the speed of the fan using a drive, the current range can change or not be accurate on the low end of the curve. Instead, using the torque output of the drive can be more accurate on the full range of the speed of the drive to have a better threshold of when there is actually a underload condition from a broken belt. More information on how to calibrate this user load curve and details about the broken belt detection can be seen in ABB Technical Note 53. If your system includes a bypass, you may want to monitor its unique BACnet points separate from what's included in the drive. It is important to make sure that you give this device a separate device ID so that way the building automation system can discover them separately from the drive. The commonly used point in the E-Clipse bypass is the bypass mode, to indicate if the drive or bypass is in control of the motor. This is a simple feedback point to know what mode the bypass is in, instead of having to judge this by the behavior of the system with the motor running across the contactor in the bypass. Similar to the drive, you can monitor the digital inputs directly to the bypass, separate from points available at the drive. In this case, I'm again looking at the digital input default programmed for the start interlock to know the status of that safety input. The relay outputs can be commanded and or monitored for status, separate from the state of the default programming. The override status can be confirmed when a fireman's override or system override have taken control over the motor output. The hand-off or auto status of the bypass can be monitored using an analog value. It is easy to note then in graphics or programming what value coming in as an analog equals which state. Here I have it in a text box for easy reference. The E-Clipse bypass also monitors line-to-line voltage on the input side of the drive package to monitor for conditions that may require the bypass to fault or protect the system. An additional BACnet point is available that shows the average input of this voltage to monitor the condition of the voltage for your drive and or system. And another point available again could be to monitor the control board temperature of the bypass to make sure it's within its range. In this case, the bypass board is reporting the temperature in degrees Celsius instead of percent of limit like the drive, so I have noted that here as a reference. If you have an ultra-low harmonic drive like the ACH580-31, there are additional points available on the line side control unit that can show values such as the input power coming from your grid or supply. This can be useful to measure directly at the drive the quantity and quality of your incoming power. With that, you can also measure directly coming into the source of the drive the kilowatts that the drive will use to supply the fan or pump. You can kind of think of this like a built-in sub-meter for that equipment, providing information towards your energy management system instead of having to have additional communicating sub-meters for each piece of equipment. If your utility happens to track kVA instead of kW, you can see that as a separate point as well. Separate from the drive inverter temperature, you can read the line side converter temperature as well. This again will be in percentage of the fault limit for the line side unit. And here are a couple examples of the percentage to show what you will see when related to hitting the warning or fault limit. Finally, with the ULH drive, you can write to a value called user reactive power reference. With the latest firmware, this point is available to command an adjustable value of kVAR or percentage to allow for power factor correction from the active front end of the ULH. Trends or data logs are a very useful tool for troubleshooting events that happen over time, or looking back at historical information to understand the operations of your system. For looking at drives, it's great to monitor when exactly faults or warning conditions might happen and relate that to other things happening in the building, such as units coming online or events happening local to your area. You can monitor the output of the drive in relation to the fan or pump to see if there are changes in current, torque, or power to get a better understanding if changes are happening to the system itself, such as variations in the ductwork, the amount of load in the building, filters starting to get dirty. You could also monitor incoming power from the grid to make sure that there's no fluctuations that relate to faults in your equipment. You may have noticed I have a couple of trend logs spread around the programming as we've been looking at different points. Here I'm showing a log over time of the DC bus voltage, and here is a trend of the analog input 2 that you could have wired as feedback for a PID loop control. You may see the data on a graph or chart, and that can help relate it to other values if you're comparing multiple points. Depending on the control system you're using, these will look slightly different, but overall provide similar amounts of information in such a way to help determine the status of your total system. When it comes to variable frequency drives, energy savings opportunities is always a major consideration when designed into a building automation system. Not only are there significant energy savings opportunities by being able to vary the speed of the fan or pump application, trending the data for power output can be a troubleshooting opportunity as well. Comparing multiple air handlers of similar size or design to each other, it can be easy to see on trend logs if one system is having to use more energy than another. When comparing the entire building's energy usage to the behavior of a single system, you can start to identify if there's a reason why overall energy usage for the building may be related to an air handler or a pumping system. Being able to diagnose these issues quicker can lead to additional energy savings by keeping the building operating at optimal efficiency. So, to summarize, building automation system graphics are a powerful tool to understand the status of your HVACR system. Variable frequency drives are a critical component to add better control and cost savings by reducing energy. Monitoring these devices and their operations can significantly impact the operations of your building and the troubleshooting opportunities. We looked at the BACnet object available from a variable frequency drive, which objects are a must-have to provide control over a communications network, which objects are optional but very useful to increase your understanding of your building system, and the capabilities of collecting trends or data logs to see historical data about the performance of your HVACR system. Thank you for watching, and as always, reach out to your local ABB representatives if you have any other questions.